Welcome everyone. My name is Saikari and I'm excited to talk to you today about network X-ray vision, harnessing eBPF for cloud-native observability superpowers. We are embarking on a journey to explore how this powerful technology, eBPF, is fundamentally changing how we observe and understand our cloud-native environments, essentially granting us observability superpowers. As organizations increasingly adopt containerization and microservices, particularly with Kubernetes, the networking layer, that invisible mesh connecting everything, becomes incredibly complex. It often turns into a critical blind spot for operations and SRE teams. We find that standard monitoring tech tools frequently struggle to provide the necessary depth and real time insight required in these highly dynamic systems. This talk aims to demystify eBPF, which stands for Extended Berkeley Packet Filter, and demonstrate how it provides deep, surgical visibility directly from the Linux kernel itself. A key advantage we'll explore is how it achieves this level of detail without imposing the typical performance overhead we often associate with traditional methods like deep packet inspection or extremely verbose logging. Over the next 20 to 25 minutes, my goal is to bridge the gap between this powerful low-level kernel technology and the practical, actionable strategies you can implement in your own environments. Let's first clearly define the problem we are addressing: the Kubernetes networking blind spot. In cloud-native architectures, especially when employing service meshes or dealing with hundreds of microservices, the communications pathway between them become incredibly intricate. These invisible connections and complex dependencies are often dynamic and not fully captured by static configurations or even infrastructure as code definitions. This is where traditional monitoring approaches often fall short. Many rely on sampling, grabbing data points intermittently, or aggregating metrics over time. While useful for high-level trends, this inherently loses the fine-grained detail needed to understand transient issues or the exact sequence of events during network problem. This leads to limited visibility. Operation teams are left grappling with troubleshooting challenges, trying to diagnose complex distributed issues without detailed real-time insights into the actual network traffic flow between pods, services, and it's like trying to debug a tangled mess of wires with the lights partially off. So what is eBPF? How it helps us see through this complexity? eBPF stands for Extended Berkeley Packet Filter. While the original eBPF was primarily for filtering network packets, eBPF is a revolutionary technology that acts like a lightweight, sandboxed virtual machine inside the Linux kernel itself. This allows us to run custom, event-driven programs whenever specific kernel events occur, like network packets being processed, system calls being made, or kernel functions being entered or exited. This kernel-level integration is key. We are getting data right from the source. The extended part signifies its programmability, going far beyond simple filtering. This enables surgical precision because eBPF programs run in the kernel context. They can access data structures and react to events with minimal overhead, capturing detailed information at microsecond resolution without relying on sampling. Think specific protocol details, latency measurements for individual requests, or specific system calls related to network activity, all without the heavy cost of traditional packet capture or tracing tools. Crucially, eBPF prioritizes safe execution. Before any eBPF program is loaded, it undergoes a rigorous verification process by the kernel. This verifier checks for loops, out-of-bound memory access, and other potential issues to ensure the program cannot crash or compromise the kernel. This safety guarantee is what makes eBPF suitable for running directly in the production systems at scale. Let's crystallize the differences by comparing eBPF-based monitoring side by side with more traditional methods. Looking at data collection, traditional approaches typically use sampling at intervals or rely on agents, pulling metrics periodically. eBPF, in contrast, performs continuous event-driven capture directly at the Linux kernel level. This fundamental difference significantly impacts performance. Traditional agents, especially those doing deep inspection or relying on user space processing, can introduce noticeable overhead. eBPF, being kernel native and highly efficient, boasts a near zero performance penalty for many observability tasks. Then there is visibility depth. Traditional monitoring often provides aggregated or service level metrics useful for but often lacking granularity. eBPF allows us to dive much deeper, accessing packet level details, system call information, and fine-grained latency measurements. Implementation also differs. Traditional methods often involve deploying user space agents or sidecars, while eBPF integrates directly with the kernel, often managed by a platform or agent that leverages kernel capabilities. Finally, real-time analysis. Traditional methods are limited by their collection intervals, whereas eBPF can observe and react to events at the microsecond level, enabling true real-time insights and even automated actions. The shift to eBPF isn't just an academic exercise. It delivers tangible, significant improvements in real-world operations. One of the most dynamic impacts consistently reported is a massive reduction in mean time to resolution (MTTR) for network-related incidents. Organizations frequently see MTTR slashed by over 70%. Complex, baffling issues that previously took hours or even days to diagnose can often be pinpointed in minutes with deep visibility eBPF provides. Beyond reactive troubleshooting, eBPF empowers preventative detection. By continuously monitoring granular network behavior and establishing baselines, teams can detect subtle anomalies like increased latency, unusual connection patterns, or rising error rates before they even escalate into user-facing outages. This real-time visibility enables proactive responses and adjustments. Furthermore, this deep understanding of network traffic directly translates to cost optimization by precisely identifying inefficient communication patterns like chatty services sending unnecessary data across availability zones or external networks. Organizations can optimize traffic flow and resource allocation. As mentioned, one enterprise saved over $200,000 annually by optimizing cloud networking costs based on this eBPF insights. A standout capability enabled by eBPF is the ability to automatically discover and visualize the intricate web of service dependencies in real time. Because eBPF sees all network traffic at kernel level, it can build a complete topology map of which services are communicating with other, how often, and with what latency. This is incredibly powerful because it often reveals undocumented legacy or simply unexpected relationships that aren't defined in Kubernetes manifests or service discovery systems. We move beyond static diagrams to a live view of reality. We can also perform temporal analysis, watching how these dependencies and communication patterns evolve over time. This helps understand application behavior under different loads or during deployments. By analyzing traffic patterns like data volumes and communication frequencies, we can pinpoint bottlenecks, identify overly chatty services, or discover opportunities for caching or communication optimization. Crucially, eBPF allows us to trace complex dependency chains. We can follow a request as it hops between multiple services, even across different namespaces or clusters, providing the true end-to-end visibility needed to troubleshoot distributed systems effectively. eBPF continuous granular data stream is perfectly suited for sophisticated real-time anomaly detection. The process often starts with baseline establishment, where eBPF-powered monitoring systems observe traffic over time to learn what constitutes normal behavior for specific services and communication paths. This could include typical latency ranges, error rates, protocols used, or connection frequencies. Once a baseline is established, the system performs deviation detection. It continuously compares live traffic against the learned baseline, automatically identifying statistically significant deviations or abnormal patterns without requiring engineers to manually set and maintain potentially brittle static thresholds. When an anomaly is flagged, eBPF provides rich contextual alerts. Instead of just saying high latency detected, an alert might be specific like latency between service A and service B increased by 300 milliseconds, affecting the specific parts via this network path. This context drastically speeds up diagnosis. Furthermore, this real-time detection can trigger automated response mechanisms based on predefined rules or specific traffic patterns detected by eBPF. Example, a sudden surge in DNS errors. You could trigger automated workflows for remediation, like restarting a pod, rerouting traffic, or collecting more detailed diagnostics. Adapting eBPF might seem daunting given its kernel-level nature, but there are practical approaches to get started. The key recommendation is to start small. Don't try to boil the ocean. Begin with single Kubernetes cluster, maybe even just a specific namespace or application. Focus on addressing a particular pain point first, perhaps improving troubleshooting for a critical service or simply mapping the dependencies of complex application. Next, you need to select tools. There's a vibrant ecosystem. Open source projects like Cilium, which uses eBPF extensively for networking and security. Pixie from New Relic, focused on auto-instrumented observability, or Hubble, part of Cilium for network visibility, are great starting points. Commercial platforms often build upon these, offering more integrated experiences, longer data retention, and enterprise support. You will need to enable kernel support. Most modern Linux distributions and cloud provider images support the necessary kernel versions, generally 4.18 or later for broad features, though newer is often better. Ensure your nodes meet the prerequisites for the tools you choose. Finally and crucially, integrate workflows. The insights from eBPF are most valuable when they feed into your existing process. Connect the data to your primary observability platforms like Grafana, Datadog, etc. Integrate alerts into your response systems like PagerDuty or OpsGenie, and use the visibility to inform your CI/CD and deployment strategies. Let's illustrate the potential with the real-world case study from the demanding financial services sector. A global payment processor dealing with stringent performance and reliability requirements implemented eBPF-based observability across their extensive Kubernetes platform. They were facing challenges managing the complexity of over 200 interdependent where network issues could have immediate and significant financial impact. The results were striking. They achieved 70% faster troubleshooting. Critical payment processing issues, which previously could take hours of painstaking log creation and guesswork, were now consistently resolved in minutes thanks to the granular visibility provided by eBPF. They gained complete visibility into their service mesh, successfully mapping the intricate dependencies between all 200 plus microservices, uncovering previously unknown interactions. Perhaps most impressively, they leveraged eBPF capabilities for automated remediation by detecting specific network anomaly patterns in real time. They were able to trigger automated self-healing actions for approximately 85% of common network issues they encountered, significantly improving platform resilience. This case highlights how eBPF delivers not just insights, but also enables automation and improves stability in complex mission-critical systems. While operational stability and faster troubleshooting are major wins, eBPF also unlocks significant cost optimization benefits. By providing unparalleled insight into exactly how your network resources are being consumed. A major driver for cloud costs is often network egress. By providing eBPF to precisely identify and quantify traffic flowing between different availability zones or out to internet, organizations can pinpoint inefficiencies. Optimizing these cross-zone traffic patterns based on eBPF data has led to substantial savings, with examples showing reduced egress costs of up to 43%. Similarly, eBPF can reveal unnecessary or overly chatty communications between services that might be consuming valuable CPU, memory, and network bandwidth. Eliminating or optimizing these communications, guided by eBPF insights, leads to lower resource usage overall, sometimes by as much as 28%. Furthermore, having precise real-time visibility into actual service traffic loads enables much faster scaling decisions. Instead of relying on coarse-grained metrics or guesswork, you can right-size your deployments based on observed demand, leading to more efficient resource utilization and potentially faster scaling actions, improving both cost and performance. One report indicated 52% faster scaling decisions driven by these precise insights. Hopefully, you are now seeing the potential of eBPF and wondering how to get started in your own environment. Here's a practical path forward. First, learn. Dive into the fundamentals. There are fantastic resources online. Check out, like example, eBPF.io, vendor blogs, conference talks, and documentation for specific projects like Cilium or Pixie. Understand the core concepts like probes, maps, the verifier, and common use cases. Second, experiment. Theory is great, but hands-on experience is the key. Set up a non-production environment, maybe a kind cluster on your laptop or a dedicated dev cluster. Deploy some of the open source tools we mentioned. Try instrumenting a sample application and explore the data you get back. Third, measure. Once you have something running, quantify the benefits in your context. Can you troubleshoot a known issue faster using the eBPF data? Can you identify an optimization opportunity? Gather metrics to build a case for wider adoption. Finally, once you have demonstrated value and built confidence, you can scale. Plan a phased rollout to your production environment. Integrate eBPF observability strategically into your standard operating procedures. Start small, learn, and then scale with confidence. So, that brings us to the end of our exploration of network X-ray using eBPF. We have discussed the challenges of observability in modern cloud-native systems and seen how eBPF offers a powerful solution by providing safe, efficient kernel-level visibility. We have touched upon its real-world impact, from drastically reducing troubleshooting times and enabling proactive anomaly detection to visualize complex dependencies and drive significant cost optimizations. The key takeaway is that eBPF is no longer just a niche kernel technology. It's becoming a foundational component for robust, efficient, and observable cloud-native platforms. I strongly encourage you to investigate the tools and techniques we discussed today and consider how they provide superpowers for your own team and systems. Thank you for your time and attention.